So welcome everyone to this mathematical physics seminar, the CRM series, and we're very happy today to have Professor Kevin Costello from Perimeter Institute to give us a lecture about celestial holography. But tell a bit about Kevin. So he did his PhD at Cambridge University, working on Gromov within invariants. And then he moved somewhere for a postdoc. So Kevin, can you refresh my mind?
I was in University of Chicago and Northwestern for postdocs.
That's right. And after that, he moved to Perimeter, where he's now the Krembil's Foundation William Rowan Hamilton Chair of Theoretical Physics. So that's a long name.
Yeah, that comes with all the money comes with all the long names.
That's right. The longer the name, the more money. So Kevin has money. And he received a few prizes. So Kevin is Irish, I gather.
Mm-hmm.
And so he received the honorary member of the Royal Irish Academy. He also got the Eisenbud Prize for Mathematical Physics of the American Mathematical Society, AMS. He's a fellow of the Royal Society, and he also got the Berwick Prize of the London Mathematical Society. So Eric's work on mathematical aspects of string theory and quantum field theory have been celebrated many times. And so it's an honor today to have Kevin speak. And Kevin, the floor is yours. So
okay, thanks very much, William. It's really it's a great pleasure to be here virtually, although it would be nice to visit in person sometime. So what I want to talk about is something which is kind of a new direction for me. I've been studying with Natalie Paquette, who's now at the University of Washington, about the celestial holography program, which is an idea put forth by Strominger mainly and his collaborators as a new way to understand scattering amplitudes in massless field theories. And it's related to things like the BMS symmetries that you might have heard about. So what I want to talk about is a way to understand what's going on in this program by thinking about twistors, as in by using the twistor correspondence of Penrose. So I'm going to assume nobody knows anything about either celestial holography or twistors, but that people, are at least familiar with the idea of amplitudes of Yang-Mills theory. So you guys can see my screen okay and everything? Yeah. So the idea, the celestial holography program, so we're going to start with a massless field theory in dimension 4. It also works in dimension 3. And we're going to parameterize the on-shell momenta by a point on the celestial sphere. So the coordinates they like to use is say, well, you have your momentum. It depends on a complex number z and the energy scale omega. And it's written like this. And you can check that this is a null vector. So it depends on the energy omega and a point in the celestial sphere. Well, just to remind you, what's the celestial sphere? So this is a concept Penrose liked to emphasize, since the 60s. If we take the set of vectors in space, whose length is t squared, sorry, this should be squared, so that they're null vectors at a particular time, and then we send that time off to infinity. That's a sphere called the celestial sphere. You can also think of it as a collection of future light rays, which point to the origin. Now, the second description makes it clear that the celestial sphere is acted on by the Lorentz group. The celestial S2. And this is, of course, SL2C. And the action is by Mobius transformations. This is I think this is at the heart of the story, this observation. And if you go back and see what I call this coordinate Z on the celestial sphere, that's the Z which is transformed by the Lorentz group under Mobius transformations. So let's consider scattering amplitudes of our massless theory. Of course, that's some function of the momenta, and maybe of whatever other indices I have hanging around, which I'm going to suppress. What people who are studying celestial holography and related topics like to do, they like to do this thing which seems a little odd at first sight, is that they take the Mellin transform with respect to the energy. So that they look at states which are an infinite sum of states of all energy. They're no longer energy eigenstates. And once one takes the Mellin transform, we get this quantity A hat. And the idea is that you should study these amplitudes like they're the amplitudes of a 2D CFT. Okay. So it's a little formal so far. We've just taken the ordinary scattering amplitudes of any massless theory, and we performed an integral transform, and we say, oh, look, this looks a little bit like the correlators of a 2D CFT, where the momenta I'm inserting, they look like the operators of a 2D CFT, and this parameter in the Mellin transform, which appears there, looks like the spin of the operator. And which momentum I'm using corresponds to which point on the celestial sphere. This is the basic idea, and this quantity is, well, it's too early to say it's a celestial CFT. All we've done is an integral transform, but you might hope that this expression is really the correlation functions of a CFT, and that this transform, this Mellin transform, this is called is at the heart of the celestial holography program. So what they want to do is just understand amplitudes in this new basis. So the justification for saying it's a bit like a CFT is that the Lorentz group acts in the two-sphere. So once I've done this Mellin transform, the Lorentz symmetry of ordinary amplitudes looks a lot like the global conformal symmetry of correlators of a CFT. I think so far that's one of the main justifications for thinking about it like a CFT. But whatever it is, the celestial CFT, if there is a CFT, is really poorly understood. It's not clear that it's an actual CFT. But even if it is, it must be some kind of exotic and strange. Okay. Oh yes, there's one more point I wanted to make. So as I said, you can think of like the Mellin transform as it being applied to the amplitude, but equivalently, you can imagine that you're scattering states which are no longer energy eigenstates, but that I've taken an ordinary energy eigenstate like this and performed some Mellin transform with respect to the energy to the state. And then if you fiddle around with it, it looks a lot like this field sourced by a local operator on the celestial sphere. So these correlators are not too different from thinking about local operators very far away based on points of the celestial sphere and the OP, so on between. Okay, before I move on, are there any questions?
Yes, conformal in what dimension?
Yeah, so you mean like the dimension by the,
well,
what dimension is the operator?
Well, you're saying it's conformally invariant, and I'm asking, this is not acting on the null cone, it's acting on this melon transference space. So what is it acting on a three-dimensional space?
No, it's acting on the two-dimensional space. So what we've done is we've taken the null cone, like the positive null cone, and divided by dilations to leave us with a sphere. So it's acting on that sphere.
Okay, and you're thinking of the sphere through stereographic projections, the complex plane, I guess.
That's
And
right.
then,
So like,
and then it's Möbius transformations in the complex plane.
yes, I mean, what else could it be? I mean,
Okay,
it's
so it's really
isomorphic.
SL. So the conformal group is SL2C,
Exactly.
or G, yeah, SL2C or PSL.
PSL2C is more accurate, yes. But that's a very formal statement. I mean, the Möbius transforms are simply the conformal symmetries of the twistor. So, and obviously the conformal symmetries of the twistor are kind of obviously SL31. So,
Are you assuming that you're in the center of mass frame, so the sum of the p's is 0?
no, because you want to have, let's see. I suppose when you take the amplitude, oh man, of course the amplitude, there will be a delta function. I have to say, I mean, this is not my program, so I'm not gonna. I'm mostly getting this by reading the papers of Strominger and his collaborators. So I hope I'm not. So if there's any questions I can't answer, you could look there. Before you take the Melon transform, the amplitude will have a delta function in it, forcing the sum of the momenta to be 0. After you take the Melon transform, it should. I've never thought about this point, but it should just be a consequence of conformal invariance, I think. Okay. Any other questions? Okay, so one thing people like to study is, and they find some nice answers, is what happens when my 2 points in the celestial sphere come together. In CFT, that will be momenta. Let's say that we were studying a CFT, I'd be taking the OB of local operators. And we would like to have a celestial sphere kind of scattering amplitude version of this. So in terms of momenta, when the two z's come together, two momenta become orthogonal on the external lines of my amplitude. Because if I write my momenta in terms of, turns out the inner product behaves like this. Sorry, where's Z I minus ZJ? The inner product is like the norm of the distance, the difference between the two z's in these spaces. So of course you can always imagine what in any amplitude you might expect singularities when two nearby momenta become orthogonal, because then in the middle here, look at this diagram, there can be a null momentum in the middle. Wrong things. So what people have computed, and the answer is really nice, is that sometimes when 2 points in the celestial sphere come together, our two external momenta become such that their sum is null and you can exchange a massless particle. Sometimes there's a nice kind of OB. And the regime in which it works really nicely is I have to work with gravity or gauge theory, and I'm taking, let me go back a little bit. My incoming states here are all of positive helicity, and the outgoing state is also of positive helicity. So it's like the vertex. This is like a plus, plus, plus. So in this case, one has a really nice answer. If I just took a vertex with a plus and a minus, it's a bit messy. If I took a loop level, some kind of loop level collapse, nobody has any idea what goes on. So when they do this in gauge theory or gravity, they find there's a first order pole which only depends on z and not z bar, just like in a chiral CFT. So they find out at tree level, if we study positive velocity particles only, the celestial CFT, if it exists, contains a nice chiral algebra, which means there's infinitely many symmetries. Yes?
Can I ask a question? This is a statement about gauge theory scattering amplitudes of positive velocity states?
Yes, at tree level.
At tree. So this is a tree level gauge theory statement.
Yes. Mm-hmm.
But you're still saying something, so it's the tree level 3-point function of positive velocity states?
Yeah, well, I mean, yeah, two are coming in, one goes out, one's going out, yes.
Okay.
So it's not, a super deep calculation.
Right.
It's a very nice answer.
But it's not preserved at the loop level?
This is kind of the whole question, right? So my expectation is that no, but it's not being proved. In the literature, people have studied loop level soft theorems, and they have there are results that for like energetically soft particles, there's no loop corrections. But this is a slightly different context, and it's not clear if the energetically soft results apply here.
And is this an OP, like in a normal 2D CFT, you expect convergent operator product expansion in the sense that you could take any pair of operators, even at finite separation, and replace them by, expand them in a basis of local operators. When you say OPE, do you mean OPE in the sense, like, I should be able to take Zi not equal to Zi plus 1, but near it, and still expand in this basis of local operators? Or do you just mean, this is a statement about scattering amplitudes in gauge theory only in the limit where they coincide?
I'm only confident in this statement if we expand in series when they're very close. It looks like this singular term plus regular terms. I don't really know whether the regular terms converge or not.
Okay, thanks.
Okay, so where were we? So this nice papers of Guevara, in which Peyton Stromager found that these scattering processes are encoded by certain chiral algebras. But they're very, very big chiral algebras. They're Cas-Moody algebras for infinite dimensional Lie algebras. So what does that mean? If I have a finite dimensional Lie algebra, to build a Cas-Moody algebra, I look at loops into it. Here I'm going to look at loops into something that is already infinite dimensional. So what they find for gauge theory, I'm going to take the Cas-Moody algebra for the Lie algebra of polynomial maps from C2 to G. In other words, the symmetry algebra is kind of like this huge thing. It's like a triple loop algebra. I have 3 variables, but only one of them is inverted. And here, like V1 and V2, they transform under SO4 in some way. And for gravity, there's another kind of really pretty answer. It's also the Cas-Moody algebra, but for an infinite dimensional Lie algebra. What's this infinite dimensional Lie algebra here? Call it Ham of C2. It's the Lie algebra area preserving vector fields of the plane. I'm writing things in terms of C2 because I'm thinking of everything as being analytic functions or holomorphic. But this is just, You write down a vector field on the plane and you ask it has no divergence. That's some giant Lie algebra. Okay, so we're let to. So what have we understood so far? We've done this noun transform. It looks like a CFT. And at tree level for positive velocity particles, we find some really nice answers for the OPs. But the natural questions one can ask. So as an outsider in this field, the first thing I might think of is, when we think of holography, we're equating two different things. Each thing has an independent definition. Gravity equals gauge theory. Here we only have one thing. We've just taken scattering amplitudes and reformulated to something like a CFT. So you can ask, does the CFT have an independent definition? Maybe at a more basic level, when we study holography, if I wanted to find something like a 2D CFT or a chiral algebra, I might like to study the boundary of ADS3. And there is no ADS3 in this picture. There's OR4 or OR3-1. One can ask, does this really lovely OPE work beyond tree level and beyond this plus to plus scattering? Well, my take would be Yang-Mills theory is really, really, really hard. This is just an integral transform of the very, very hard problem of finding the scattering amplitudes of Yang-Mills theory. It seems to be too much to ask that this nice pattern would persist all orders. But if that's the case, one would like to have an explanation for why this positive velocity part is so nice, you want to explain why the positive velocity part is so nice, and you want that explanation to not work in general.
Question, the gauge coupling constant appears nowhere. Is that right?
I mean, you can put it into this vertex if you want to. But
okay. Right.
Yeah. I mean, you don't have to. You could just reabsorb it into a rescaling of the states.
Okay.
Okay, so my answer to these questions would be that if you think about twistors, all of this becomes much cleaner. You can explain in a really nice way why this particular OB is there. You can see that there really is something like ADS3, and this really is a boundary chiral algebra by using a certain twistor transform. So let me remind you a little bit about what twistors are in the background. So twistor space was introduced by Penrose in the 60s as a way of studying massless field equations and massless field theories in form. So it's a complex manifold, which is this description. It's the total space of O1 plus O1 over CP1. And one of the nicest early results is the Penrose War correspondence, the 70s. This tells us that in the self-dual limit, we can write Yang-Mills theory as a holomorphic theory on twistor space. So what's the self-dual limit? The self-dual limit of Yang-Mills theory, it has an ordinary gauge field, and it has an adjoint valued self-dual 2 form, and this simple BF action. So it's called a self-dual limit because if we add on another term, I can add on this term in brackets. We add on Yang-Mills coupling times B squared plus this term, then we can integrate out b squared and get the full Yang-Mills action. So this is some kind of degenerate limit of Yang-Mills theory. And what Penrose and Ward showed is that it's described by a very simple theory on twistor space, holomorphic BF theory, where I have a gauge field, which is a 0, 1 form of twistor space, and a kind of conjugate field, Lagrange multiplier field B. The Lagrangian is simply BF again. And later, Penrose, in his like nonlinear graviton construction, showed how to do this for self-dual gravity as well. So the reason this is going to be relevant is that the scattering process we've mentioned, this plus plus to plus, it's the same thing for self-dual Yang-Mills and ordinary Yang-Mills. If you were to write it down and using this Lagrangian, this b squared term would not appear when I was studying the plus plus to plus scattering. It would appear if I was studying plus plus to minus, or anything with any minuses. So this suggests that we can explain the fact that these OPs are really well behaved by using twistors. And similarly for gravity. So the main result I want to explain is that we can use this twistor correspondence to transform self-dual Yang-Mills to a 3D theory in such a way that the celestial chiral algebra, studied by Strominger, Guevara, Imich, and Pate, is exactly the boundary algebra of the 3D theory. So for me, that's an explanation of why that is so nice. So let me explain. So we're going to start with self-dual Yang-Mills in R31. And we're going to move up to twistor space. Twistor space is 6-dimensional.
Sorry, when you're saying twistor space, you mean the space of alpha planes of self or anti-self-dual two planes?
Oh, let me see. I mean,
and that's what the Ward-Penrose correspondence is.
Yeah, that's right. But you know, people have different perspectives on twistor space. I'm trying to remember that one. So, my definition would be this, but yes.
Well, these because there are different notions of twistor space. There's,
I mean, it's an open
structures and so on. But you're speaking about twistor space the way it's used in Yang-Mills theory with respect to self-dual Yang-Mills, and my understanding is that it's P3.
Yeah, absolutely. This is an open subset of P3. But I don't want to talk about S4. I want to talk about R31.
Yes, yes.
So I've removed the line of infinity. But yes, absolutely, it's P3.
Okay. Okay.
Okay, so where are we? So we start with self-dual Yang-Mills theory in R31. Penrose and Ward say we can lift that to a theory on twistor space. Now, twistor space is 6 real dimensional. So I can take a patch, which looks like S3 times the positive reals times C. I mean, another way to write this patch is in complex word language. It's like, you know, I can choose 3 complex coordinates locally. And I'm asking that one pair of them is non-zero. And then I do KK reduction along the 3-sphere, and I get a 3D theory. So kind of similar to how one might think about, it's kind of similar to ADS 3 times S3. So here.
Sorry, could I just say, I'm not sure if this is the right way to understand it, but it seems to me that you're doing secretly a complexification and a realification in the background, because you're starting out with null cone, I mean null momenta. But if you complexify, then instead of null lines, you get null 2 planes. Those are the alpha planes. So everything becomes complex. And that's what the twistors in general correspond to, because the alpha planes are not in the real, they're not in the real tangent space. They're in the complex.
Yes, no, yes, you're exactly right. And if you look at these papers on celestial holography, the first thing they do is they say, oh, my Z and Z bar are actually independent.
Right, right.
So then for each Z, as I vary Z bar, I get the null plane you mentioned.
So in the usual Ward-Penrose correspondence, one takes the self-duality conditions and interprets them as holomorphicity conditions over P3, which is
exactly.
But you are taking a real 3D. When you say 3D, do you mean real 3D?
Down here, yes. Well, what I'm doing is I've done what you said, and I've gone up to this complex three-dimensional space. And let me go to the next slide. So my complex three-dimensional space is these coordinates, say Z, V1, V2, because I'm working in a patch. And I'm writing it as a real three space times a three sphere. So the S3, it's like the unit, let's see how to say this. So for each Z, as you said, for each Z, I have a null plane. That's kind of, these are the coordinates on that null plane. And I take the unit vectors in that, and that's a three sphere. So I'm left with the value of Z and the radial correction. Does that make sense to you?
Sort of. I'm not sure where the real three sphere is coming from. Oh, so I think I do. So CP3, you're thinking of some sort of vibration, or?
Yeah, I'm working in a patch which is just C3.
Yeah.
And I'm writing C3 as C times C2. And the real three sphere is just the unit three sphere in C2.
Yeah.
And then I'm left with the radius of C2 and the other coordinate.
Okay, I'm not sure what the details are, because you're doing it locally. I usually think of it globally, but
no, yeah. Globally, it's kind of annoying because it's some S3 vibration or something. I didn't want to write that.
Okay, but the self-duality conditions are translated into holomorphicity conditions of the vector bundle over CP3. But so when you take this sort of reality condition, I'm not sure what the holomorphicity means.
That's a really good question. So let me, so in general, so at the level of the equations, we have some holomorphic bundle on CP3, but I want to think of that as a classical holomorphic field theory, where the Lagrangian, I wrote it on a different side, looks like BF02A. These are fields in twistor space, and the variation of B imposes the fact that A defines a holomorphic bundle. So something like this is the Lagrangian for a holomorphic theory, and that just means topological theory is one where there's no stress energy tensor, or the stress energy tensor is Q exact. A holomorphic one means the stress energy tensor associated to motions in the anti-holomorphic directions are Q exact. So that's what we found. So then you're right that if I take such a thing and reduce it on the three sphere to give me a three-dimensional theory, you'll find something funny. You'll find a mixed holomorphic topological theory. So fortunately, for some completely different reasons, I had been studying exactly such theories, me and other people, with Mina Ganajic and Carmen Vafa and Jake McNamara. We have a paper about them. And we studied them further with David Agioto and Tudor Dimofsky. And so I'm going to use some, okay, so what have we done? We've used twistor transform to translate self-Julian mills into a three-dimensional theory. The three-dimensional theory behaves holomorphically that way, and it behaves topological in that way. And Davide and Tudor and I, well, for some different reason, we were interested in studying the algebra of boundary operators. Just like the kind of thing one would do in ADS 3 CFT, and you can study them by a version of Witten diagrams. And what's really nice is that if you apply this to the three-dimensional theory you get as the twistor transform of self-dueling mills, you find the same chiral algebra as Guevara, Himrich, Page, and Stromer applied. It's like just on the nose the same. Okay, maybe I would like to, since I'm not sure this is super clear, so I just wanted to add a page and explain something about so for gauge theory, chiral algebra, it looked like the Lie algebra GV1, V2, Z is the inverse. Well, you notice this is equal to holomorphic gauge transformations on a patch of twistor space. So this is so even without doing any work, one can see the Penrose-Ward correspondence, which tells us self-duality equations are related to the holomorphicity equations, immediately implies that the chiral algebra found by Strominger and his collaborators can just be seen right away from twistor space. And there's similar kind of easy remark for the gravity sector too. Okay, maybe I'll pause. Are there any questions?
Well, you mentioned non-self-dual Yang mills, but you really are only talking about self-dual, right?
Absolutely, yeah. I mean, my opinion is that you will never get a nice answer for full Yang mills. It is just way too complicated.
But you know this is very, very old stuff, but actually when Witten first appeared on the scene, it was exactly how to deal with full Yang mills in a twistor-like way. Way back in 1978, before you were born.
I was one.
Oh, all right. But there is a twistor correspondence, but it's really, it was actually due to Yaskin and Eisenberg. And well, anyway, it's called ambitwister, but it really is complicated because it is not just a straightforward correspondence. You have to have formal neighborhoods and extend the space somewhat. And what Witten actually pointed out was that it becomes exact if you superize everything.
Yeah, I know a little bit about ambitwisters.
Actually, I mean, I thought you were going to ask about the other Witten paper from like 2004, where there's the string theory on twistor space that's supposed to describe perturbative Yang theory. Is there a relation? Is this a limit of that story?
Yeah. So if you were to take so what he does is, if you take some kind of holomorphic Chern-Simons on CP3/4, that corresponds to the self-dual limit of n equals 4 Yang mills. The same kind of thing.
Mhm.
This is a local QFT in twistor space. But if you take holomorphic Chern-Simons, we add on some non-local terms. We get full. So this is the entire problem. So everything I've said works perfectly fine for n equals this self-dual limit of n equals 4 super Young-Mills. And we get a lovely chiral algebra. That's great. But once I've destroyed locality in twistor space by adding on these other terms, I mean, if I have a non-local theory, what can I do? It just doesn't make any sense anymore to try to talk about the boundary algebra. Okay.
Thanks.
So let me move on to my next slide. So what have we learned so far? So after doing this twistor transform, we found something a little similar to the usual holographic story, where we get a CFT by studying the algebra of operators in the boundary. But something important is that the bulk theory we found does not include 3D gravity of any kind. So I would very much hesitate to describe any bulk boundary correspondence where the bulk does not include gravity. That's not really holography in my book. The reason is, what we've done, the gravity case, we move from 431, go up to twistor space, and we do a KK reduction along the 3-sphere. The result is some gauge theory for SL2, it's higher spin stuff. But the SL2 that appears is the one that acts on the internal 3-sphere. It is not the SL2 that rotates the complex line. This tells us also that the boundary chiral algebra does not have a stress tensor. One can see this explicitly by noting it would contain things like a Cass-Moody at the critical level. Though it's not really a 2D CFT, it's part of a 2D 3D system.
And there's no Sugawara construction. I mean, you have a Cass-Moody algebra, so you can't just build a Sugawara stress tensor and try and use that.
Yeah, but it's at the exact level where the Sugawara construction fails.
Sorry, how does it fail?
Oh, I'm not going to be able to pin it down exactly, but if the OB is at the critical level, when you write down the Sugawara construction, you have to divide by something, and sometimes the thing you have to divide by is 0.
Okay, I guess I need to remember that. Okay, thanks.
So this is, I mean, it's interesting. People have studied this in other areas. You get an algebra which is a very large center. The center is the W algebra.
Okay, thank you.
Mm-hmm. So next, let's look at our other questions. Well, why does the plus to plus OB work so well? And here I would say it works really well because the self-dual theory is very simple and can be captured by the holomorphic geometry of twistor space. Now, suppose we wanted to go further, to either go beyond tree level or to look at negative velocity particles. Will something nice happen? And, well, I can't prove that it doesn't work, but I can say that this approach just fails. So the story breaks down unless we use some very, very special theories which are written as local theories in twistor space. Almost nothing can be written like this, and full Yang-Mills cannot be. So as I mentioned, to deform from self-dual Yang-Mills to Yang-Mills, we add on a B-squared term. And this B-squared term is non-local on twistor space. It's like a bilocal expression. I'm integrating over pairs of points in twistor space, which correspond to the same point in O3, 1. So if I was to transform this into the three-dimensional perspective by KK reduction along twistor space, you would find a perfectly nice local theory as before, but some kind of weird bilocal term. And now, I just don't know how to make sense of the boundary algebra of operators when I have a non-local bulk term, just because once I've destroyed locality, there's no reason that my correlators will have singularities only when points coincide. The correlators could have singularities anywhere. So we conclude, this approach fails when I move to full Young mills. It seems to only work for theories that are local in twistor space. Sorry, William, how much time do I have left? Oh, you're muted?
Sorry, I said about 10 minutes.
Okay, thanks. Good. So, there are very few local theories in twistor space that work at the quantum level. So, almost any 4D Lagrangian you can write down for a massless theory will be some kind of nasty multi-local expression of twistor space. But there are a handful that do work. So let's start with this self-dual Young mills. Okay. One might think that the Penrose-Ward correspondence tells us self-dual Young mills corresponds to a holomorphic local field theory in twistor space. This is certainly true classically, but unfortunately, there's a one-loop gauge anomaly on twistor space associated to this rectangle diagram. And the anomaly, if I take the gauge variation of this diagram, I get some expression which looks like that, where chi is the gauge parameter. So you should think of this rectangle anomaly as being very similar to the triangle anomaly in O4. So even in this case, it appears that at one loop, something seems to go wrong. There seems to be no nice chiral algebra, and something bad happens to 2-to-2 positivelicity scattering. So I have to say, this is kind of hard to compute directly. So, like the twistor analysis suggests, we're not going to get a nice chiral algebra. I find it quite challenging to start from space-time and compute the scattering process, see what happens when my two incoming momentum become collinear, and see what kind of singularities you get. But I'm trying to work at that. However, maybe just for my last slide, it turns out that we can modify self-dual Young mills to cancel this anomaly. There's a twistor space version of the Green-Schwarz mechanism. It's really a topological string, a close cousin of a topological string Green-Schwarz mechanism, whereby we add on an additional field in twistor space, and the box anomaly is cancelled by an anomaly from a tree-level diagram. So this can happen when we have this Lie algebra identity. Perhaps if you're familiar with the original Green-Schwarz mechanism, there was a similar Lie algebra identity which was necessary to make it work. So this Lie algebra identity holds for SL2, SL3, SO8, and all of the exceptionals. And it it turns out what you find is something kind of interesting, but a bit odd. Self-Julian-Mills plus an axion there's some very particularly tuned coupling constant here, and a fourth order kinetic term. So my conclusion is, I don't know how to build a nice loop level chiral algebra describing scattering, even for self-Julian-Mills. But I do once I've added on this kind of weird axion. And then there are more exotic cases where we can also cancel the anomaly. But I don't want to take up your time by talking about them. Okay. So I'm going to stop there.
All right. Thank you, Kevin, for a very nice lecture.
And thanks, William.
So we had a few questions, but I'm sure there are more questions. So the talk is open. So if anyone wants to ask a question, please raise your hand or speak up. I have a question. So if no one is asking, let me go with my question. So Alex was also asking about the applicability of this beyond tree level.
Mm-hmm.
And so you're pessimistic about whether this would work even for Yang-Mills generically. And so what's the next step in this program? What's the big goal that you would see, since you want to apply it to generic gauge theories? Where do you think there? I'm trying to grasp the usefulness for physicists.
Let's see. So I think what's going on is like I'm not really part of the community who are been working on this. I came into this because I noticed that one can explain the algebras they find in a very simple way from twistor space.
Mm-hmm. And so people haven't used this analogy with twistor space in this program before, is that?
Not to my knowledge. I mean, there's something Lionel Mason was looking at, but I'm not sure similar to what we're doing or not. It's a little surprising because if you've studied twistor space, it's kind of clear that their algebras are just the same ones that appear in as gauge symmetries in twistor space. That's a really simple observation.
Mm-hmm.
So you can say in some ways I'm a little bit of a skeptic of the program, and what I'm trying to explain is why I think it's a bit too hard to see. I mean, if you accept that twistor space is the most natural explanation for why the nice things that have been found work, you can also see twistor space as an argument against things working further, because only this sector works at twistor space.
So yourself, do you have ideas you would like to develop in this program, or you essentially on this note going to move on to other things?
I mean, I think what I would like to do is to say, like, I'm going to give up in full Yang-Mills, right?
Mm-hmm.
But that's not the only interesting four-dimensional theory. I'm interested in four-dimensional theories which display features of integrability, such as this one, self-Julian-Mills plus this Vertexian term. And there are more complicated ones. So my take would be, it's too hard, just like we were studying two-dimensional systems. You might have some random Lagrangian, you're never going to get the full control of the scattering amplitudes. But if you have an integrable one, you can. So my take would be there are some very special 4D theories whose scattering we could possibly control by some integrability-like structures, similar to those present in 2D. So that would be the direction I'm aiming at.
Okay. That's fair enough, yeah. Okay, thank you.
Mm-hmm.
Do we have other questions?
So the examples that you wrote down here on the slide, these are all gauge theories in 4D.
Mm-hmm.
Are there any examples involving the, you said 4D gravity at tree level was related to the algebra area preserving diffeomorphisms.
Yeah. So
are there any analogous constructions motivated by Green-Schwarz?
There are related things. So one thing I don't know how to do is if you take what Penrose and so if you take Penrose's nonlinear graviton construction, you can write it down in some field theory in twistor space, and then you can try to compute the anomaly of this box diagram. I found that computation quite challenging, and I wasn't able to do it. So I actually don't know if there's an anomaly there. But there are other examples where if you take a topological string on twistor space, like an honest topological beam model, then there's a more familiar, more standard Green-Schwarz cancellation. And what you find is like topological string, it becomes some kind of 4D, for some reason it's a 4D sigma model plus a dynamical scalar. So there are examples which include something kind of gravitational, but it's not represented as a metric, but as a Kähler scalar.
Okay, thanks.
There's a phone. Maybe there's a question on the phone.
Hi, Kevin. Am I audible? Or
yeah, you are, yeah.
When you say so, I mean, you're kind of, I guess you didn't assert directly that the OPE doesn't work, so to speak. But what do you mean when you say that, like, you think beyond tree level, the OPE wouldn't work? Like,
so what I'm concerned about is that let's see. Like if we have let's think about what happens if you have a non-local theory in twistor space and what can go bad. So kind of bad things that might happen. You could have singularities when Z is not equal to Z prime. Well, those are just different. I don't know how to exclude that. I don't know how to prove that happens either, but this is the kind of thing that might happen if you have a non-local term in twistor space.
Right, but then, so like, would that already in, like, for example, the Mellin transform version of a 4-point amplitude, you're getting things like delta Z minus Z bar. I mean, does that constitute, I guess, a bad singularity? I mean, it's not even, you don't even need an OPE to see stuff like that happening, right?
Delta. So you got like a delta function at C minus C bar.
Right. I mean, if you just take like that's actually a universal feature of the celestial CFTs for 2-2 scattering.
Oh, I didn't know this. A 2-2 scattering at tree level or 1-2?
I just anything, because what happens is for example, if you imagine you have your definition was like Mellin transform of an amplitude, and inside that amplitude there's a delta function that's like the one that makes sure that p1 plus p2 plus etc. is equal to 0, and that gives you an overall like delta z minus z bar that multiplies the entire thing. So this is for 2-2 scattering in 4D, and then if you go to like, for example, 2-3 scattering, you don't have it anymore, right? Physically, it's like momentum conservation, right?
Yeah, I mean, I try to square this with the way I was understanding this, because like if we're taking the self-dual theory at tree level, then it seems I mean, does this only happen when there's like positive and negative velocity particles for gauge theory?
No, I think it's quite universal. Like it happens for scalars. I think it happens for gauge theory. I could be wrong, but I'm pretty sure it's like basically just momentum conservation, right? Because I'm pretty sure this delta z minus z bar just comes from saying that the scattering can happen in a plane, basically.
Right.
Right.
Let's see. But this does seem like something that would exclude a nice chiral algebra, as far as I can tell. And I think we're not going to get to the bottom of this right now. I think I need to understand what you're saying. Who is this? Sorry, I didn't catch you.
Oh, it's Justin Culp.
Oh, okay. I mean, would this exclude a chiral algebra?
I have no clue.
Okay.
So are you still thinking about a question, or?
Oh, I'm waiting for other questions. I feel like I can't really
Sorry.
respond in real
Hard
time.
to say with these small icons. So I think I don't see any questions, and we have quite a few. So it might be a good time to thank you again, Kevin, for your nice talk, and thank you for answering the questions.
Thanks, William.
And we'll look for the follow-up and archive with these integrable 4D QFTs and their twistor space presentation.
If I ever get that finished, yes.
I'm sure you will. Thanks, Kevin, and hopefully we can see you in person at some point.
Mm-hmm. Okay, bye.
Bye-bye.